let's see the concept of virtual memory. Okay, so what is mean by virtual memory? What is mean by virtual address? What is mean by virtual address space? Okay, so virtual memory and virtual addresses is actually belongs to our process only. Okay, our process only. So this particular process, until now what we said, the C, it will be divided into some particular addresses. Okay, the size of the process, what we said, it's called logical memory. Size of the process is called logical memory, and the addresses that is generated by this, for this particular process, that means CPU generated addresses, we call it as logical addresses. Correct? Okay, then when it comes to your main memory or physical memory, main memory or physical memory, the addresses that belongs to main memory, we'll call it as physical addresses. Physical addresses. Okay, or it is also called absolute addresses. So this particular conversion of logical address to physical address will be done by memory management unit. Memory management unit. But this particular virtual address, when do we call a CPU generated addresses as logical addresses and CPU generated address as virtual address? Both are belongs to our process only. Okay, so there is a difference when you generate physical address. When you generate physical addresses at the time of program compilation, or at the time the program is loaded into memory. That means at the time of compilation, that is at compile time and at load time, if we generate the physical addresses, then these addresses will be called as logical addresses. Logical addresses, that means we are able to generate, memory management unit can able to generate all the physical addresses corresponding to logical addresses at the time of compilation and loading. Then we will call those addresses as logical addresses. But the problem here is the process is divided into set of pages. We have seen there are several pages. It will be divided into several pages. The memory of a process is divided into several pages, and we have seen that particular 4 GB of process, a large address space, it will be divided into almost 2 to the power of 20 pages. That is almost 1 million pages. Almost 1 million pages. And the problem here is we are unable to load this particular 4 GB, entire 4 GB memory into our physical memory, that is our main memory. Okay, so what we will do, we load only few pages. We load only few pages into main memory, into main memory. And there are a lot of pages that are not loaded into main memory, that means the programmer thinks that the entire process has been loaded into main memory, but in reality we are loading only some portion of the program. We are loading only some portion of the program, and remaining program, the it is resided in our secondary storage only. Okay, it is resided in secondary storage or backup disk. That means our hard disk drive or solid state disk. That means the actual entire process is actually stored in our secondary storage. Some pages will be loaded into main memory, and remaining pages, they are kept in our secondary memory. When CPU has generated a logical address corresponding to that particular process, if that page, okay, that particular page is available in main memory, then its physical address will be generated, and the byte that is corresponding to this particular address will be accessed. But if there is no page available, that particular page is not available in main memory. Most of the times the page may not be available in the main memory. Okay, where it is available on the hard disk, where it is available on the hard disk at that particular time. You need to load that corresponding page from hard disk to main memory, from hard disk to main memory. That means user will think that entire process is loaded in main memory, but actually it is not loaded in main memory. Entire process is not loaded in main memory. Only some part of the memory is loaded into main memory. Okay, some part of the process is loaded into main memory. That is the reason this memory, even though it is stored in the secondary storage, this memory we will consider it as virtual memory. We will consider it as virtual memory because physically it is not available in the physical memory. Okay, it is virtually available in the physical memory, and addresses that are corresponding to this particular virtual memory we are called virtual addresses. Virtual addresses. There is one more scenario where we will call this virtual addresses because see, the program in its lifetime, it will increase, it will increase at the time of running, at the time of running. So virtual addresses, okay, virtual addresses, when you call a CPU generated address as virtual addresses, when you the physical addresses are generated at runtime. Physical addresses are generated at runtime. We will call them as virtual addresses because there is some data. See, this a process started at 0 and ends at maximum. Let us take 4 GB or 8 GB or 16 GB, whatever it may be. Then it starts from its 0 and this particular memory will be divided into pages, will be divided into pages initially. And if there are any temporary variables or temporary memory will be there, that will be stored in the stack. And if that particular code will generate any additional data at the time of running, the program is running while executing, there is a chance that some particular new data will be added, some particular new data will be generated, and that particular data is also part of your process only. But where it will be stored, this particular running data, okay, running the program is running, the data is generated, then the size of the memory will be increased. Look at this heap. At the time of running, that is dynamic memory will be allocated. Okay, stack will store temporary data. So stack will be stored from top to bottom, that is it expanded from top to bottom. Heap will be expanded from bottom to top. So the data that will be newly generated or created, the size of the memory will be increased, the size of the memory will be increased, and this particular pages will also have a frame. This is also stored in the frame whenever the CPU generated the particular address. So these pages, okay, the memory where we are actually given to this particular process at the time of running program execution, program execution. So for this particular memory, for these particular pages, the physical addresses will be generated only at the running time, not at the compile time, not at the load time. Okay, then that particular addresses we will call it as virtual addresses. So all these addresses is also called as virtual addresses. See, look at this particular large hole of memory, large hole of memory. Okay, so the blank space between the heap and stack, okay, it is a part of our virtual address space, but it will require a physical pages in the main memory. Okay, so as this particular heap and stack grows, then you will get one extra page, you will keep on getting one extra physical page in the main memory. Okay, so the virtual address space that includes the holes, we will call it as sparse address space. We will call it as sparse address space. Okay, so and one more thing, when we want to link the libraries, okay, the inbuilt libraries or dynamic link libraries, when we want to load one particular process loads the system libraries, okay, or it wants to communicate and share with other process, that is also will be possible with this particular virtual addresses, and because that memory will also be allocated at the runtime. Okay, right. So sparse address space is beneficial when this particular memory is grows dynamical. Okay, so The simple thing that we can say that whenever the CPU generates an address, if you can convert, that is if you can generate the physical address at the time of compile time or at the time of load time, okay, compile time or load time, those addresses we can call it as logical addresses. But if the physical addresses are generated, the memory management unit generate the physical addresses at the time of running the program, that is at the time of execution, those addresses we'll call it as virtual addresses, and that particular memory we'll call it as virtual memory. And the sum of that particular process, the total virtual sum of all the virtual addresses, the group of all virtual addresses, we will call it as virtual address space. Okay, so this virtual address space is possible with swapping. Okay, possible with swapping of pages. Okay, also called demand paging, also called demand paging or lazy swap, demand paging or lazy swapping technique that enables the virtual memory, okay, in the operating system. Okay, so let's see some points about virtual memory. What is virtual memory? It is a technique that allows the execution of processes that are not completely in main memory. Okay, so virtual memory involves separation of logical memory from the user perspective to, okay, physical memory. Logical memory from the user perspective, logical memory is separated by physical memory. Okay, so this separation allows extremely large virtual memory, okay, to be provided for programmers when only smaller physical memory is available. That is, each process may have 4 GB, but the entire physical main memory will have 2 GB to 4 GB. Okay, so using virtual memory, we don't have any physical memory constraints. Okay, programmer can write a large programs and can install, user can install large programs. Okay, so this particular virtualization technique can increase CPU utilization and throughput, but it will not increase turnaround, decrease turnaround time and response time. Okay, so here we are not storing the entire process into main memory, we are only storing less memory related to a process, that is few pages are loaded into main memory, we require very less IO. Okay, so this particular virtual memory technique will benefit both system and the user. Okay,